Singleton bound basically says that for a given linear code with its parameters n, k, and t, the sum of its dimension and the minimum distance can be at most n plus 1. And we will prove this statement by using linear algebra. And in order to prove that, first we consider a subspace which contains vectors from fq to the n that has coordinates 0 after the indices I is bigger than d. And indeed for every vector in E, we can easily observe that it has weight at most d minus 1, because we know that at least by the definition, we know that the first only d minus 1 can be non-zero. Hence, this shows us indeed it has trivial intersection with C. And on the other hand, since it has vector dimension over fq is d minus 1, and since it has trivial intersection, the dimension of their direct sum will be the sum of the dimension of E and the sum of the dimension of C. Indeed, this is d minus 1 and k, and since this sum is a subspace of fq to the n, this dimension is less than or equal to the dimension of fq to the n. And indeed, this shows us the desired inequality. And here, as I mentioned before, this bound is independent from Q. And this also shows us there's a trade-off between the minimum distance and the dimension of a code. So that means there's a trade-off between the code verse we can store and the error correction or the detection capacity. In other words, given ND, K can be at most n minus d plus 1, or given n and k, its minimum distance of the code can be at most n minus k plus 1. So also it says that as k is large, d is small, and vice versa. And the other thing I want to point out is that as an advanced topic, actually there are various bounds which shows the relations between the parameters of the linear code. And one of the bounds is called the linear programming bound. And it is used in the optimization indeed. And it will be indeed a generalized version of the Singleton bound, or we can say that Singleton bound is a special case of this bound. And if the parameters of a linear code attains this bound, so when we get the equality, we say that our codes are in some sense optimal, and such codes are called MDS codes, maximum distance separable. So that means it corrects the maximum number of errors given its size and length, or given dimension and length. And indeed, when we introduce the algebraic geometric codes, we will see that if the length of the code is less than or equal to the cardinality of the base field plus 1, we will see that there exists an MDS code over FQ for all dimension K. However, there is a famous conjecture which claims that an MDS code cannot have length larger than Q plus 1. So the conjecture, an MDS code, is roughly speaking, this is known as an MDS conjecture. MDS conjecture, which roughly says that an MDS code cannot have length larger than Q plus 1, except in some very special cases. And one of the important results about this conjecture was given by Simon Ball, if I'm not pronouncing wrongly. And he shows that this conjecture holds over prime fields FP. And finally, about the coding theory, the last topic I want to mention is about obtaining new codes from old. Indeed, if you open any course, any book, any textbook on algebraic coding theory, you will come across several methods like the partitioning, shortening, or the direct sum. And in this case, you may check the Huffman Place fundamentals of error correcting codes. However, in this for the algebraic geometry course, we will consider only one method that will be a way to obtain a linear code from FQ, from a linear code which is defined over an extension field FQ to the n. And for this motivation, we will consider three types of construction. The first one is subfield subcode. So always we are in the case that a linear code over the extension field is given. Here FQ to the m denotes the extension over FQ of degree n. And when we consider its intersection with FQ to the n, we will denote it by series direction FQ, and we will call these structures the subfield subcode of C. Or equivalently, we can also say that the restriction of C to FQ. And indeed, we can also observe that its minimum distance in this case cannot be less than or cannot be less than the minimum distance of DC, and its dimension can be at most the dimension of C. And the second construction we will consider will be what is called the trace code. And for this purpose, first, let me define the trace map. Maybe you can be familiar with this map. Actually, if you take a course on finite fields, probably you should know this spatial map, which is defined as the sum of the conjugations of the elements, and it is FQ linear, and this is onto. And indeed, we can introduce a new linear code by taking the trace of the coordinates of a given code word from C. And this is called the trace code. And obviously, subfield subcode also has length n. And in this case, the trace code also has length n. And similarly, as a nice exercise, the dimension of 3C is at most m times the dimension C. But to conclude something about its minimum distance, it will be difficult. On the other hand, one of the nicest relation we will see later was given by Delsart. Indeed, it tells us the orthogonal complement or the dual of the restriction codes of C indeed is nothing but the trace of the dual, here the orthogonal complement with respect to inner product on FQ to the M, but here we take the inner product on FQ. And the last construction will be what is called concatenation. In this case, we will consider some FQ linear injections from given the finite field FQ to the M into n-dimensional, capital N-dimensional vector space over FQ. And for given linear code C over FQ to the M, we will introduce pi C by regarding the images of the coordinates of a code word C. And indeed, we can see that it is different from the first two codes we defined, subfield, subcodes, and trace codes. It has length. It has larger length in this case. So its length is the multiplication of n times capital N, and it has dimension n times k. And moreover, if we represent image pi, or if you consider this image pi as a linear code with parameters capital N, M, and D prime, we can also see that this is called a concatenated code. And in this case, we can also see that its minimum distance is bounded below the multiplication of the minimum distance of C and the minimum distance of image pi. So this is all what I want to say about the general information on algebraic coding theory. And in the next lecture, we will begin to see how we can use tools from algebraic function fields.